Hello. All right, we're live. So today we're going to be talking about quite implications and conditional statements. This is section 3 of chapter 6 for those of you following on in the text, and this is probably the most important sort of concept in formal or propositional logic. It's especially important, here in this modern world because it's essentially the mathematics that undergirds all sorts of computer operations, which themselves run primarily on binary logic or solely on it, really. And conditional statements are statements of the form if P then Q. That's pretty terrible. So if P then Q. So statements of this form are that of if some condition is satisfied, hence the conditional part of this, then Q occurs, Q is implied. So a good example of a statement like this would be if it rains, then I will get wet. And formally, we would write this sentence out in our logic operations as P implies Q. That would be the way we say that, where rainings, if it rains, that's going to be my P, and I will get wet, that's going to be my Q. And this would give me P implies Q here. So, as usual, we want to sort of whip up a logic table for what the for the operation P implies Q. And so we're going to lay out our a kind of series of P's and Q's here, all the possible combinations between P and Q. And we're going to ask ourselves, for which of these things does P imply Q, will P imply Q be true? Now, again, while we go through this, we kind of want to concretize it with some example. So let's kind of keep this real life example in our head as we work with the formal P implies Q. So, I claim if it rains, then I will get wet. Okay. If it rains and I get wet, was I telling the truth? It does seem so, right? If it rains and I get wet, then this statement feels fully realized. So yeah, that seems right. I would be telling the truth, and then it would be verified by the fact that it's raining and I'm wet, right? If it rains and I don't get wet, was I telling the truth here? Well, no, right? Because the whole point of the sentence is that that raining causes me to get wet, and if raining doesn't cause me to get wet, then this statement here is invalid. So in this case, this would be false, right? Well, what about this case here? This case is it's not raining. I still get wet. Is that a true statement? Now, a lot of people struggle with this one a little bit, but this actually still allows my implication here to be true. So, my sentence here is a sentence about what happens if it rains. It doesn't say anything about what happens if it doesn't rain. So, if it doesn't rain, then really, I can get wet, I cannot get wet. It doesn't matter, right? Because I didn't say what would happen if it didn't rain. I just said, hey, if it's going to rain, then I'm going to get wet. And since it didn't rain, then pretty much anything goes. So whether or not it rains or doesn't rain, I still didn't violate this statement here. So maybe another way to think of to think of the implication thing as like a promise, right? And then just ask yourself if you broke the promise by any of these conditions here. So let's say you tell yourself, if I get an A on this test, I will buy myself ice cream as a reward or something like that. And so if you got an A and then you went ahead and bought yourself ice cream, then that's great. And that's exactly what your sentence here implies. If you got an A on the test and you didn't buy myself ice cream, you broke your promise to yourself, right? You said that you would buy yourself ice cream if you got an A, and you got an A and you didn't buy yourself ice cream. Well, that's no good. If you didn't get an A, well, then it doesn't matter, right? You can buy yourself ice cream or not. Nothing in here says anything about what would happen if you didn't get an A. So either way, whether you buy yourself ice cream or not, you didn't break the promise that you made to yourself, and so you're fine. All right. Some of these colors are pretty bad. The green was not so bad the other day, but it's pretty bad now. Uh, let's get rid of that. So, when we're looking at this thing though, we should think to ourselves, well, hey, it's false under one very particular circumstance, right? It's false um, exactly when P is true and Q is false. Otherwise, this thing is going to be true. So it's worth asking then, what other statements are like that? Well, our or statement is also a statement, right, that is false under exactly one circumstance when both things are false, right? And then true every other time. So can I rewrite P implies Q as some kind of or statement? And goes back to the notion of equivalent statements that we talked about in the previous lecture or video. So I claim that P implies Q is equal to not P or Q. And we can verify this fairly easily. I'm going to tilt this a little bit. We can verify this very easily by just building the truth table for not P or Q and comparing it to this. So my first step here would be not P, which is false, false, true, true, and then not P or Q. Well, let's see. Well, one of them is true, it's true. When they're both false, it's false. When they're both true, it's true. And when one's false and one's true, it's true. So not P or Q does in fact have the same truth table values as P implies Q. And so we have the formal equivalence here, which wasn't very hard to show. Is it intuitive? Does it make sense that not P or Q in our heads that matches up with P implies Q? So here I have, if it rains, then I will get wet. If that's my P and that's my Q, not P or Q is something like either it doesn't rain or I will get wet. Right? Doesn't rain is not P if P is raining, and getting wet is still Q. Right? So either it doesn't rain or it will get wet. Well, if it doesn't rain, then whether or not I get wet, that's true, right? And that's what happens down here. If it does rain, then the only way this could be true is if I did get wet. So if it rains, I had better be getting wet, and that's this first case here. If it doesn't rain, if it does rain, so this is false, and I don't get wet, then this whole thing was a lie, right? It rained, and I didn't get wet. Neither of those things happened. And that's this case here, right? It rained, but I didn't get wet. And that would make this sentence here false. So there we go. That is gives us an intuitive sort of connection between the logical equivalence between these statements and some concrete example that shows us that these things are the same. So what's the point of that? Well, previously when we were talking about equivalence statements, we talked about how De Morgan's law helps us break down equivalence statements, especially when we have a bunch of negations going on. And so let's talk about what the negation of something like P implies Q is going to be, right? There's certainly statements like this that are not true. Like people make these claims all the time in real life, and you've probably made some yourself. I know I have, most likely. And so you'd want to be able to take a statement like that and say, okay, what's the negation of that? What's the opposite of if it rains, then I will get wet? And the fact is that we don't have to do something super crazy to figure out what the negation is, because we know P implies Q is equal to not P or Q, and we know how to negate things like this with De Morgan's law. So let's say I want to negate P implies Q. Well, that's the same thing as negating not P or Q. Then by De Morgan's, I can distribute the not through, and I get something like not P and not Q. And I hope we can all agree that not P is just P, and not Q, well, it's just not Q. So the negation of P implies Q is P and not Q. And so what's the concrete version of this? Well, if it rains, then I'll get wet. What's the opposite of that? What's the exact opposite statement of that? It's probably that it rains and I don't get wet, right? That well, you say this thing's gonna happen, and whenever it rains, and then it rained and it didn't happen, so you're lying. And so again, in the language of the P and Qs you have here, P and not Q is the sentence. It rained. That's my P, and I didn't get wet. That's my not Q, right? So if this happens, then you can go to the person who made this original sentence here and say, hey, you lied. You said if it rained, then I would get wet. It rained, and it didn't get wet. The statement is false, and that's the negation of that. All right. Um, so knowing that these things are equivalent helps us to break down exactly when implication statements are true and also to find the negations of implication statements. So, as a sort of exercise, let's take a sentence that has multiple parts in it, turn it into a logic statement, simplify it, and negate it. So let's start with a sentence. Let's say, if it's sunny and I'm in a good mood, then I will take a walk. So if it's sunny and I'm in a good mood, then I'll take a walk. So a sentence like this seems like it has a couple of pieces in there. There's certainly an if then component to it, right? But the hypothesis or the initial thing that's conditional seems to be an and statement, right? You have to be sunny and in a good mood in order for this thing to activate. So if you're sunny and in a good mood, then what it implies, if you satisfy that condition, is that you'll take a walk, right? So let's see. If sunny is P, good mood is Q, and take a walk is R, right? Then I can rewrite this whole thing to be the sentence P and Q implies R. All right? Do we feel good? All right. Then if I want to simplify that, if I want to say, I do want to know exactly when this thing is true, but I don't really feel like messing about with the implication and the weird sort of statement there. I'd rather rewrite this in terms of and or statements, which would be easier for me to look at. Then I should just note that this thing is equal to not P and Q or R, right, by the fact that we just shown before I erased the board. And then I could break this down further with the Morgan's law and say, well, that is not P or not R, sorry, not Q or R. So either I'm going to be in a bad mood, or sorry, either it's going to be not sunny, or I'm not going to be in a good mood, or I'm going to take a walk. And any one of these things would make the statement true. So this is a statement that's true as long as any of this stuff here is satisfied. Now, if you want to parenthesize this because this was parenthesized here, that's fine. But it really does mean the same thing. It might help a little bit for what's going to happen here. Now, let's write out this thing though in terms of P, Q, and R as a sentence. So let's say it's either it's not sunny or I'm in a bad mood, or I'll take a walk. All right. And we can ask ourselves, why is this the same thing as that? Well, here you said if you're sunny and you're in a good mood, then you end up taking a walk. So here, if it's not sunny, you're not obligated to do anything up here. So whatever you said up here wasn't a lie, right? If you're in a bad mood, then you're not obligated to do anything you said up here, and you're free to do whatever you want otherwise. But if it is sunny, and you are in a good mood, so neither of these things are true, then in order for this to not be a lie, R has to be true. In other words, you need to take that walk. You said if it's sunny, in your good mood, then you'll take that walk. And so the funny thing about this is, as long as you take a walk, you're good, right? It doesn't matter if if it's sunny or not, or if you're in a good mood or not. As if you just force yourself to take the walk, no matter what, then you will have satisfied this statement, no matter what the mood or sunny conditions are. And so that's the or are part here. Any other circumstance like uh, not being sunny or being in a bad mood automatically invalidates this condition, right? And once this is not satisfied, you're free to do whatever you want. And that's how you should view the implication. That the hypothesis, the conditional part here, is something that forces something else to happen. And if this thing doesn't happen, if this thing is false, anything that you do is fine because you didn't restrict yourself to something like that. You didn't restrict yourself uh, at all. You didn't say what you were going to do if it wasn't sunny or if you're in a bad mood. So you're not held to anything as a result. Okay. Let's say this person is lying. Whoever made this claim was not telling the truth, and this is false. Then we want to negate that statement, and we can do so by negating this thing here. So the negation of P and Q implies R is equal to the negation of not P or not Q or R. Again, because this and that are the same thing, right? They're equal to each other, so I can make this replacement. Then by De Morgan's law, I can distribute my not through, so I can say that this is not P, not P or not Q, and not R. And then De Morgan's law lets me distribute the not through here, so I can say that's not P and not Q and not R. And then not P is P and not Q is Q, and then we have not R. All right. So if this person was lying, if whoever made this claim lied, then what exactly is going on there? It means for that to be a lie, it's sunny and you're in a good mood and you don't take a walk. Then you'd be lying, right? That's you said that if those things happened, then that would if you said those things happened, then you would go take that walk, and they happened. You didn't take the walk. You lied. So we can write this out as it is sunny, and I'm in a good mood, and I didn't take a walk, and that would negate what you had originally said. Here. All right, so for the final part of this, I'm just gonna list out a uh, a bunch of equivalents, a bunch of algebraic rules for logical statements. We've touched on some of them, and some of them are implied, and some of them are just common sense. But just for sort of complete listing of things that you're allowed to do, I'm going to make a list of them here now. So, thing one, P or Q is equal to Q or P. P and Q is equal to Q and P. These are what we would call commutative laws. And these just make sense, right? If I eat breakfast or lunch, that's the same as eating lunch or breakfast. If I eat breakfast and lunch, it's the same as eating lunch and breakfast. That's obviously the same. Okay. The second thing is associativity laws. So P or Q or R is equal to P or Q or R. P and Q and R is equal to P and Q and R. And these are associativity just like in standard algebra. And so we should know also in standard algebra, these all have to be the same operation, right? Like A plus B plus C is equal to A plus B plus C, and A times B times C is equal to A times B times C. And we mix times or plus with each other, then we get different rules for that, right? And so let's do that. Let's think about what happens if we mix our operations. So if I have like A times B plus C, I'm allowed to distribute that product through, right? And so something very similar happens here. We get P and Q or P and R. We can distribute this operation through both terms. And you can check this with truth tables if you ever feel so inclined. But what's neat about this is that, you know, products distribute over sums, sums don't distribute over products, right? 2 plus 3 times 4 is not the same as 2 plus 3 times 2 plus 4, right? These things are different. But these aren't regular and and or are not the same operations as plus and times. They're fundamentally different things that deal with fundamentally different structure, right? P, there's infinitely many numbers. There's only two logic values. It's a really neat thing. So, kind of surprisingly, the operation is double distributive, meaning if I have P or Q and R, I can go P or Q, and that's my and there, or P or R. That's super cool. The next law, just making sure I have enough room here, is De Morgan's law. So I already know what that is. Not P or Q is not P and not Q. Not P and Q is equal to not P or not Q. Number 5, here is absorption laws. So right, this is distributivity. This is De Morgan's. So absorption either one of these, if you operate it with itself, you're just gonna get itself back, right? If I have lunch or I have lunch, then I have lunch. If I eat lunch and I eat lunch, I'm eating lunch, right? Those are nonsense statements. So Sorry, I missed. These are idempotent laws. The namings of some of these get to be a little wonky. So then now the absorption laws. If I have a statement P and Q, and on top of that, I allow that's like either P and Q happens or P happens. Well, that's not really adding a lot of information here, right? And the only way that if P, so let's just think about what happens here. If P is true, then it doesn't matter what happens to Q, right? The whole thing's true. If P is not true, then this is not true, right? Then if P is not true, then that's false, and this is also false, so the whole thing is false. So it doesn't matter what P does or what Q does, right? It only matters what P does. If P is true, the whole thing's true, and P is false, the whole thing's false. Um, and then similarly, if I have P or Q and P, well, if P is true, then that's true, and that's true, so the whole thing's true. If P is false, then the whole thing automatically becomes false, right? Because that's false. So again, P is the only relevant thing in that whole statement. Right? 7, not P is P. That's called the double negative rule. And we know what that means. If I don't avoid something, then I'm doing that thing. So, great. All right. And then we get to some of the ones we've touched already. P implies Q is not P or Q. And so here's an interesting one. P implies Q is the same thing as not Q implies not P, and this is called the contrapositive. And this is a very useful one in mathematics because when writing proofs in mathematics, sometimes you want to prove statements like this, but this equivalent statement is easier to prove. So, if it rains, then I get wet. Would we agree that's the same thing as if I don't get wet, then it didn't rain? That seems like it makes sense, right? Like if raining makes you wet, then if you're not wet, it couldn't have rained. That has to be a consequence of that. So that this falls from that and that these would mean the same thing just makes sense, right? If you want, you can go ahead and do truth tables for these statements, or you could rewrite them using this fact here, right? You get not P or Q, and you get not, and then you get not Q or not P, and we would see that those are the same thing, right? So number 10, P or true is true. P and true is P, right? And we know that these have to be true. If you have an or statement, one of them is always true, then it doesn't matter what P does, the statement is true, right? On the other hand, if it's an and statement, then if P is true, this is true. If P is false, this thing is false. So this thing does the exact same thing that P does, right? And we have similar conditions for false. If we have P or false, well, this is automatically false. So the truth of this depends on what P does. If P is true, then this thing can be salvaged. If it's also false, then the whole thing is false. So all we get is whatever P does as a result. P and false. In this case, it doesn't matter what P is, whether or not P is true or false. Because of the false here, this thing is forced to be false. And finally, we get these identities. If either P or not P is allowed to be true, then that's always going to be true, right? So it's if it'll either be raining or not raining. Well, that seems like it would always have to be true, right? I can't think of a circumstance where you could do that. I will either eat breakfast or not eat breakfast. Yes, those are your options. On the other hand, I'm going to eat breakfast and not eat breakfast. No, that doesn't seem like that's something you're allowed to do. So there are no circumstances that would allow that statement to be true. So that would always have to be false. So there we go. This is an outline of all the algebra rules related to logic statements. And if you master these rules, then you won't ever have to write truth tables out, though truth tables will always be an option. I'm going to make a second follow-up video to this about circuits just for that section alone because it is a slightly different idea. But circuits are a very powerful and important application of binary logic because, well, circuits are how all of electronics are powered, and they're powered on the basis of these rules. So thank you very much. I'll see you later.